where was the problem? The problem is trying to take these terms at the boundary. What if we were to sort of force it not to? So what do I mean by that? Take the same function we had there. But now, what it wanted to do is when I went down here, as I broke it up into evenly spaced points, down here it really started oscillating. But what if I clustered my points at the edge? In other words, I said, let me cluster things here. The middle seems to be no problem. I'll cluster more here. So when it starts coming down here and wanting to wiggle, I don't let it, in some sense. Okay? Well, here is the natural clustering you want. The Chebychev points. Goes from -1 to 1. And when you now define the polynomial, same as before, on Chebychev points, because of the way you've clustered this, basically your fit is fantastic. It just kind of like totally gets it. No polynomial wiggle. And there's some kind of deep-seated reasons for this, by the way, and I'll give you a reference if you want to look it up. But basically, the argument here is it wants to start going, and then now you say, no, no, you have less time to meet this point. You can't go taking off on me. Before it could. Oh, I've got to hold dx to the next point. I think I'll go on a trip. Okay? Here it says, oh, I got to meet, oh, and then every time it wants to wiggle more and more towards that boundary, and you just say, I've got to point closer and closer and closer. You tie it down. It has to come down here. It's kind of like a little constraint. And by the way, you don't need a whole lot of points in the middle because it has no problems in the middle. So you put it on this domain, it does a beautiful job. And that is, I have that figure in the notes there, and if you look at it, because I can't project up there, you'll see this. It's right there. You can see how well it does, especially against the other one. So this is interesting, right? So it says, hey, you know what? I can think about now polynomials, because by the way, what's nice about polynomials, right? If you're going to start working with them, they're really easy to differentiate. You kind of have this intuitive sense of how they work, and you're just evaluating on just different points now. Instead of evaluating on equally spaced points, you just do it on the Cheb points, Cheb collocation points, and you're done. Method 3.
So to clarify, we're not converting to a polynomial because these are somehow for applying the spectral methods. We're converting it because polynomials are fundamentally easy to deal with.
Yeah.
Okay.
So polynomials are very easy to deal with, and now what we found is they're very easy to deal with, and they especially like Cheb points. And so now we're going to start talking about, oh, so, so when I drew that drawing in class yesterday with Smackdown, right? What we know is spectral will win every day of the week until you hit the boundary condition. So all these lectures are really about like, okay, is there a way that our big guy who has all the advantages in life, can we give him even more advantages in life? And the answer is yes. Right? It's just like the real world. Okay? All right. So this is kind of in some sense, how do I work hard? So I had this weakness, which is I couldn't handle very many boundary conditions. And now I'm going to try to fix it up by saying, well, hey, if I work on Cheb points and I can still do this, I can do any boundary conditions I want on these points. Oh, and by the way, I know that this connects to the discrete cosine transform, so I'm back to spectral, am I not? So that's the main idea, is that now we can go back and connect it to Cheb, because we're on the Cheb points, and we're going to build everything from there. Yeah?
The reason that the polynomials are not good at the boundaries, and they're good on the center, it's because they start to satisfy the constraint from the center to go to the boundaries, or it doesn't matter, like the shape?
Doesn't even matter. So what you do is you satisfy all the constraints simultaneously. So you don't start at the center and then go out towards the edges and satisfy it. But what you do see is just at the edges. And by the way, so there's a reference I give in the notes to why that works and then why this doesn't. There's kind of actually a lot of theory of why it actually gives you the polynomial wiggle specifically at the boundaries.
What is the shape of the function?
No matter the shape of the function. Take any generic function, look at it at the edge. you'll just see huge oscillations if you try to do a Taylor fit. So here seems an option. And because now we've connected onto these points we know where that's where the Cheb lives. So what we're going to say is, oh, great, I know Cheb lives out here, so let's start setting it up, because if I can hook it up with Cheb, then I have a potential of being back to spectral, and our big guy gets one more advantage. Okay. Okay, so now I'm going to sort of build this Cheb matrix that I... Remember, this is the past. That's now the future. Okay. Hopefully that's not too confusing, John Connor. Okay. Everybody know John Connor? From Terminator? No? Okay, anyway. He's the guy that goes to the future and past. Anyway. Never mind. All right. Clustered points, Chebychev differentiation. So what we're going to do here, right, we're basically saying this. Suppose I have a function, v of x. And what we're going to do is we're going to chop up v of x. In particular, we can work on some domain, -1 to 1. And what we're going to do now is chop it up on this domain. So what I have is v of x is going to be now chop it up into a vector v on some points. In particular, we're going to use the Cheb points. Okay? All right. So now, that's first. That's what we're given. 2. What do we want to do with this? Now, what we want to do to represent this v of x, but by the way, v of x is some function we're starting off that's given to us exactly. But what we're going to do now is say, I want a representation of that function that I can work with now for doing future things, like taking derivatives or putting in ODEs and so forth. Right? So I'm going to start off with this function, cut it up. I have exact values. Now I'm going to do something with it. So what I'm going to do is represent the v of x by a polynomial. I chop it up. My polynomial is going to describe, so each point of my polynomial will be the v at that particular point. So now I have that. Now the one thing that we want to do is figure out how to differentiate this function. So in some sense, what we're going to say is my differentiated function is just this. How do I do that? So I'm not differentiating v of n. I'm differentiating the polynomial p of n. Okay? Everybody go with that? All right. So ultimately, what is this? In the way we think about things, this is simply that. Right? This is just, you take this vector, you multiply my matrix, you get back out. And we've already learned this from finite difference, right? Our matrices A, B, C, what they do is you just multiply these things out, get yourself the derivative. Okay? So the derivative, differentiation, is equivalent to matrix multiplication. And if you set up that matrix right, it just takes the derivative with some prescribed accuracy.